differentiation. The first thing in this section I want to look at is kind of explain what's meant by a function that is defined implicitly versus explicitly. Most of the time you guys have been working with explicitly defined functions. Okay, so the idea would be this one right here, that's an explicitly defined function. What that means is it's solved for y. Okay, you've had all your equations basically solved for y for them, so you just did a derivative the way that we've been working on. So explicit looks like that, it's solved for y. Implicit means it's not solved for y. So that would be the implicit form of a function like that. Explicitly you would solve that for y. Okay, and then when you do a derivative in an explicit form, that's what you've been doing. So the idea is implicit differentiation is a technique that's used for differentiating stuff like this. Now this example that I typed up here is a good example of something. If I just said, okay, okay guys, solve this for y, you would have a really rough time doing that. Okay, in fact, you wouldn't be able to do it. Sometimes you can't take functions and solve them for y. Okay, so it's better to differentiate, or you really have no choice but to do it in an implicit way. Okay, so what I'm going to do is kind of take you through the idea of implicit differentiation. Everything we do in this section is just over and over again, different examples of implicit differentiation. So the first thing that you need to get straight in your mind, and this is the whole key, is basically if you're doing the derivative with respect to x of x to the third, that's what you've been doing all semester for the last several weeks. It's 3x to the second. We know that. Okay, the variables agree. So in other words, that you're taking a derivative with respect to x, and x is the variable you're using. That's what you've been doing. This is what's new to you. So if you're doing the derivative with respect to x of y to the third, those variables don't match, do they? That's x, that's y. Well, what you do is you use the chain rule. So you still differentiate this the way you're used to differentiating it. That's 3y to the second, right? But what you have to do is multiply by dy over dx. But you just write it that way. You just write it that way. Okay? Because what you're doing is really chain rule, which is always saying multiply by the derivative of what's inside. What's inside is y. Okay? So you have to do this when you're doing implicit differentiation. Another example would be like if I did d dx of sine y. You might write this example down. What's the derivative of the sine? Cosine. Now we'd say cosine y, but you would have to write the derivative of the inside part. And you just write it that way. Okay? You don't just say derivative of y is 1, you just say dy over dx. It'll probably make a little bit better sense when I do a couple of examples of why you have to do that. You have to leave that terminology within your problem, okay? All right, so let's go down to this next page, and we'll do this a little bit, then we'll work with a couple of examples, and the examples are going to start simple and they'll get a little harder. Okay, if you look at example A, do the variables agree? X and X. Yeah, so we're going to say the variables agree. So we're just going to use power rule. Okay, so what's the answer to this derivative? Yeah, that's great. You guys got that down to a science, don't you? Okay, good. Okay. All right, how about example B? Do the variables agree or disagree? Disagree. They disagree. So in this case, what you're going to do is you're going to use the chain rule. Okay, so let's go ahead and do that derivative. So what you do is, first of all, you just do 10y to the 9th, but you multiply by the derivative of y. So you write that as dy dx. That's how you write the derivative with respect to x of y to the 10th. Chain rule. You got to add that extra feature in there. Okay? All right. So we're going to go ahead and begin to look at these things implicitly then, and kind of begin to put some of these things together. So when we do this derivative, and I'm going to write a couple more steps on this. I'm going to have you first of all just write, okay, we're doing a derivative of a sum, so we know we're doing the sum of the derivatives. Okay, so let's at least write that out, and then the rest of it we'll do in our head. Okay? All right, what's the derivative of 2x? 2. The variables agree, right? X and X agree, so it's just 2. That's what you're used to. Okay, now the variables do not agree on this, so what do? First of all, the derivative of that is 8y, but then what do? You got to add in that dy over dx. So that's your derivative. That's how you write it. Okay? All right, you'll see the point of this a little bit in a little bit here, so we're getting there. Okay? All right, does that make sense? Okay, mainly it's when the variables don't agree, and when they do agree, how you handle that. Now, this problem right here is a product rule. Okay, you have to use product rule. It's a product of two functions. So what you're going to say is the first times the derivative of the second, and I think it's real important that you write this step like that, plus the second times the derivative of the first. Okay, so that's product rule. So you've got to get that put together. Now, to finish up the problem, you've got to do those two derivatives right there. So it's all about whether the variables agree with each other or not. Okay? All right, so this is x to the third. Okay, do the variables agree with each other on this part? No, so technically you would say like this. You would say, okay, the derivative of y is 1, but then we got to multiply by the derivative dy dx. Okay, so you just write this as dy over dx. Just write it that way. Okay, variables don't agree. Okay, and then this next part of the problem is going to be y. How about on this part? 3x squared. Do you have to put the other dy dx thing? No, they agree. So that would be 3x to the third like that.
3x to the second.
Oh, second. Look at that. I can't even do the simple stuff. Okay, all right, like that. Okay? All right, does that make sense? Yeah? Okay. All right. It's not that, these aren't that hard, but you got this variable disagreeing thing is what you got to get straight. What kind of rule would you use on the next one? Okay, good. Quotient rule. So let's put it in the quotient rule. So we're going to say bottom times derivative of top. Be sure that you write it exactly like this too. Put that ddx there. Got to learn to do that exactly right. Minus the top times the derivative of the bottom, and then it's all over bottom squared. Okay, like that. Okay, so let's go ahead and do the two derivatives. Not going to do much simplification on this problem. So we're going to do that derivative, we're going to do that derivative, and then we're going to write the answer. Okay, so it's all about whether things agree or not. So we're going to write down the sign x. Okay, so what is the derivative of 3y going to be?
3 times dy.
There you go. Good. Okay, the derivative of 3y is 3, but since the variables don't match, we have to say dy over dx. You have to add that in there. Okay, now the next part is 3y. What's the derivative of sine x? Do you have to put the dy dx? No, because they agree. Okay, so it goes like that. Write the sine squared x. That's it. It's good enough. What I'm trying to do with these is prepare you for the next thing. Okay? It's just kind of get you used to when the variables match and they don't match. Okay, any questions so far? Okay. And you'll see where I'm going with this. Now, these are kind of, when you do implicit differentiation, these are the guidelines. I'm not going to go through that. I'm going to do that as I do problems. So let's go ahead and go to example 1. We should have time to do several of these things today to finish up. Okay, so the first thing is, this function is defined implicitly. It's not solved for y. So what you do, you don't try to solve it for y or anything. You just leave it in the form it is. Step 1 is what you're going to do to both sides is you're going to take the derivative with respect to x of both sides of the equation, okay? And whatever you can do in your head, you'll be able to do some of this stuff in your head, which is fine, but as we're learning this, let's kind of write the steps real carefully. So we're going to do the derivative of the left side, and then we're going to do the derivative of the right side, okay, like that, okay? Now, I'm going to break this up. I'm going to write maybe one more step than's necessary, but let's write this as derivative d dx of y squared plus the derivative of 3x equals the derivative of 8. Okay, and you could even start the problem that way if you wanted to. Okay, so what we're going to do is we're going to do each of these derivatives. Okay, so what is the derivative with respect to x of y squared? 2y times dy over dx. That's the key, all right, because the variables don't agree with each other. What's the derivative of 3x? 3. What's the derivative of 8? 0. Good. So let's move it over here. We got 2y times dy over dx plus 3 equals 0. Okay? Now, the next thing you're going to do, the second step, is you're going to solve this equation for dy over dx. That right there needs to be isolated by itself. Why? Because that gives the derivative. Okay? It will give the derivative of this function. So you can kind of rearrange things in your head. You subtract 3 from both sides. So you get 2y times dy over dx equals negative 3. Okay, like that. Now, you've got to get rid of the 2y. How do you get rid of the 2y? You divide by it. Okay, so you can divide by 2y, divide by 2y. And see, by doing this, you have the derivative of this function, and we never had to solve it for y. So we have dy over dx is equal to negative 3 over 2y. Okay, that's what we call the implicitly differentiating that function. Okay, did you guys follow that? Okay. Okay. Now we can find the slope of a tangent line. Now the slope of a tangent line is the derivative evaluated at a point. So what I've done is I've given you x is 1 and I've given you y is square root of 5. So we're just going to take this derivative. We're really doing, notationally, you can write this as dy over dx evaluated at 1 radical 5. That's kind of a good notational setup for that. Then plug it in. Well, notice your derivative does not have an x in it, so you don't worry about it. This is independent of x, so you just do negative 3 over 2 times the square root of 5, and you're done. That's the slope. One of the things about sometimes when you're dealing with differentiating things implicitly, sometimes they come out kind of simple, and then figuring out a slope or a rate of change at a particular point, sometimes pretty simple to do. Okay, so that's not a bad one. That's a pretty straightforward one. How'd that look? Okay, all right, well, let's keep pushing with a little bit more complex examples. Okay, let's run through this one for sure. All right, step 1, don't do anything to the equation. Leave it alone. Step 1 is always take the derivative of both sides of the equation. So we're going to do derivative of y squared plus xy plus 3x. Then we're going to do the derivative of 9, like that. Now we'll try to do the left side in our head as much as we can. Okay, let's just kind of take each piece one at a time. I'll try to highlight so you can kind of keep track of what I'm doing. Okay, what is the derivative with respect to x of y squared? 2y times dy over dx, right? Okay, variables don't match, so you got to do that. So that's taken care of. Okay, let's push to the next part. How do you differentiate that? What kind of rule? It's product rule. There's two things being multiplied, so we need to do the product rule on that. Okay, so we'll bring down the plus sign. We write down the first times the derivative of the second. The derivative of the second is just dy over dx. That's how you write the derivative of y is dy dx. Okay, then plus the second is y times the derivative of the first. Well, what's the derivative of x just in your head? That's 1. Okay, so that's how that goes. Okay, so that would be the product rule doing that. You know, you can write another step if you need to, but if you can do some basic stuff with a product rule in your head, you just do it. So that is first times derivative of second plus second times derivative of first. Okay, now we'll move on to the next thing here, which is the derivative of 3x. So what's the derivative of 3x? Just 3. The variables do match, so we have that. And then on the right side, the derivative of 9 is what? 0. Okay, right there. So that's your derivative. So what you have to do now is the second step is you want to go through and you want to solve this for dy over dx. Okay? So the way you want to do this is like this. Anything that has a dy over dx in it, leave it alone. Leave it on this side. Everything that does not have a dy over dx in it, move it to the other side. Okay? So that means we need to move the 3. It doesn't matter which one you move. You got to move the y and you got to move the 3. So we're going to have equals minus y minus 3 like that. Okay? Everything that has a dy over dx, get it together. Everything that doesn't, go to the other side. Okay? Now, what do you think I can do to the left side? You can factor. Okay? You can factor out dy over dx. That's a common factor, so it can be pulled out. And you have to do this a lot in implicit differentiation. That is a common factor, so you're going to say dy over dx times 2y plus x is equal to negative y minus 3. Okay, factor it. Now, you got to get rid of this part, 2y plus x. How do you get rid of it? You divide. Hey, it's all multiplied. See, that's multiplication right there. So what you would want to do now is just divide both sides by that, and then you would have what your derivative is. Okay? So for the final answer of this problem, for the derivative, you would end up having dy over dx is equal to negative y minus 3 all over 2y plus x. And that's, you could leave it alone like that. That's it. Okay? So it was really a major two-step process. So you do the derivative of both sides, then you solve for dy over dx. There's some factoring involved. Does that look okay? Okay? All right? Now, we'll finish this up with finding the slope of the tangent line. So all we're going to do on this is I gave you the point. This is a point that's on this graph, x and y. And if you graphed this thing on a calculator, that's probably it's a parabola because it's quadratic in one variable of some sort. So we just plug in. Okay, so we're going to do, and you can write if you want to, you can say dy over dx bar 2, 1. That's the best notational way to write this in Leibniz notation. And then just replace the y's with 1. And then replace the x with 2 and work out the arithmetic. Okay, so the rest of it's arithmetic. That's going to be negative 4 over 4. So that's equal to negative 1. So that's the slope of the tangent line, like that. Okay? So the idea with implicit differentiation, what you're doing is it's useful if it's real hard to solve a function for y. Okay, does that make sense? So if you can't solve something for y, this is the way to go. You can still work with the derivatives and rates of change like that. Still works out. Okay, so that'll be a good stopping point, and then we'll finish this up next time.